Hello to everybody. My name is Alvina Reihan. I'm hydrologist, my background is hydrology, and I'm going to present you today some results of our international project. It was all activities were done under the framework of cross-border cooperation program for the period 2014-2020, and together with Russian colleagues. So I don't know, is it allowed or not to show us our results, because I have no permissions from Russian colleagues, but anyway, as I'm the lead partner and coordinator of the project, I think I can show you our results. I'm from a Water and Environmental Engineering Research Group of the university, and I'm also the member of the Water Association of Estonia. So I'm represent here two organizations. Okay, some history about the problem, why we decided to start this activity. Today, my presentation is focused only on one part of the huge project results. It is development of harmonized method for our transboundary. Actually, this is a border river, Narva River, which is a natural border between two countries, Estonia and Russia. And we developed a method for Narva River discharge estimation, which suits for both countries. So it is a great challenge, actually. The first time Russian scientists agreed with our opinion, and we agreed with their opinion. So, of course, you know about problems of our Baltic Sea hazardous substances, but the main problem is eutrophication. I hope you know the phenomena arise because of enrichment of nutrients. So hydrogen and phosphorus. Where from? They come into our water body and out of our water bodies. This is our activity, phosphorus mainly, and agriculture. So it helps to our water bodies to get more nutrients and it is caused usually very intensive vegetation growth and less oxygen and not good conditions for fish. So it is these red areas. This is our Baltic Sea, and red areas show as the status of water, which is not good, just because of eutrophication. You know where from the word exists. Okay, but now back to my topic. And despite of all measures which were done by all countries around the Baltic Sea, still situation is not good. So this is a report of HELCOM from 2014 or 16, and even last reports also show as that the situation is not. It is not becoming, okay, it is becoming better, but still bad. So all red colors, these are bad situation because of eutrophication. And Narva River, border river that flows from, here is Peipsi Lake and enters to the Gulf of Finland. And these nutrients, they flow to the Gulf of Finland just through the Narva River. And if we want to reduce these nutrients, it is clear that we have to do this together with our colleagues from Russia. Well, so eutrophication is the main problem, but there are additional consequences in this region. When we want to arrange any measures for nutrients reductions, we have to do this together. And but if we use different methods and different initiatives, it is very difficult to compare this data. And this situation observes here in this area, in Narva River catchment area. And so we have each country has its own estimation method, each own data set, each own something else. And you know, Russia is not European Union country, so we use different approach also for estimation of nutrients or pollution loads. It is clear that to solve the problem, so we have to do something together. And we started our project just because of this wish to mitigate that situation. It was a long journey actually to start the activity. So we gathered together in 2016 in Narva city, and we decided to formulate our problems. Of course, it was clear. It was easy actually, because you know, if you say word eutrophication, so you will be winner in all cases. And we have found also a program which can grant such kind of problem solutions of such problems. And it was at that time Estonia-Russia cross-border cooperation program. For I said you already for this period 2014-2020, and this is a title of our project, Narva Water Management of the Narva River, Harmonization and Sanitation, but we use this Narva WATMAN. It's Narva Water Management, not WATMAN, but water management. So we started our activity in March 2019. So we set together 2016, then in 3 years, we started our activities, the next slide, and we completed it in March this year. And it was prolonged, of course, because of COVID restrictions. So this is a total budget of the project, and it is in red because it is not the truth. This was in a grant contract, but now it is another money. But anyway, this co-financing percentage, they are the same. Each partner should pay their share of co-financing. It is 10%, and program co-financed as our activities about 90% of all these monies. So we were 5 partners in the project. 3 main partners. Tallinn University of Technology is the lead partner. So partners from St. Petersburg, this is State Hydrological Institute. Maybe somebody knows it is very high methodological, hydrological methodological center in Russia. Also special company or state company from St. Petersburg Mineral, and associated partners from Narva city and Ivangorod municipalities. And our project, the long-term objective was to contribute to the good status of the Baltic Sea. Of course, when we started our project, we gathered together all stakeholders in Narva city, and the chief of Ivangorod asked us, what will you do? Will you clean the water in Narva River? We said, no, we can't. But we tried to find the scientific and practical way to do something to reduce pollutions to the Narva River and thus to the Baltic Sea, the Gulf of Finland. This is, of course, very proud objective, but we have to do that anyway. And to reach this long-term objective, we were placed our specific aims like Narva River joint water assets effective management. These words are taken from the project description, so I can't change them anymore. But actually now I think in a little bit another way. Then, of course, raising awareness and environmental cooperation increasing in the field of environmental protection, and Russia and Estonia at that time fulfill all obligations in achieving a healthy water environment in the Gulf of Finland of the Baltic Sea. So we divided our activities in 4 work packages. With communication and visibility, this is obligatory activity. So it was like a 5th and management, of course. So the first work package was dealing with development of methods for water discharge measurements in Narva River, and also runoff estimation methods. Then, of course, chemical part was also covered by our activities. Then we developed, we planned at that time to develop a water quality index for estimation of water quality. Using the same criteria in Russia and Estonia, and also we even now this share or portion of pollutions entering to the Gulf of Finland is estimated dividing these pollutions on this catchment area from Russia and from Estonia. So, and this is not objective method. As I said, I talk a little bit more in details about observations about water discharge measurement methods development and runoff estimations, and all these objectives they are now. So we started in March 2019, as I said it, and we started here. We kick-off meeting. The first meeting was organized here in Tallinn in our university. So this event gathered together specialists from Russia, from Estonia, from Finland, and it was actually proud meeting, so grand opening of the project. So, and now I completed already. Yes, now it's not final slide, but just during these 3 years, all works were done, despite many challenges, despite many obstacles, which are influenced on each people's life. And final conference, we are happy. We organized it and we just jumped in the last wagon of the train, because it was in Narva. Our conference, it was offline and online. And then during the lunch,
during 1 o'clock, we were told that.
Yes, I received a letter that it is prohibited. So, but we already on the process, so we were doing the job, and I decided to continue our workshop until the end, because we already had all results, and we wanted to show people that that we received money, but and we use them very, very optimally. So we also produced. So we produced 4 methods for different estimations, and these methods are agreed by Russian and Estonian experts. So this is the first time in our history that all researchers and even politicians were agreed with that, with our approach. And also we produced a set of recommendations, what to do in order to improve water quality or improve cooperations, etc. So, and as I was asked to tell you about runoff estimation methods, I'll do that, but also I have additional slides about some other results, because they are very, very interesting. On the opening ceremony in March 2019, when I did this opening speech, then I introduced our aims, then I expected results. When it's finished, it was 2 days actually, one of my colleagues asked me, "Do you think you will have a power to do all this work?" I said, "I don't know. Okay, let's see." Yes, but of course we were planned to do these works during 32 months, but it took time 36 months. So 3 years. Okay, the most difficult things were to measure water discharges across the river, because the border runs just in the middle of the river between Estonia and Russia. So people who know the situations know how difficult it is prohibited to cross the river. So we were asked for different permissions from border guard in Russia and Estonia. So it's officers from Moscow, from Pskov, from different main organizations were participated in this process. At least we received all necessary permissions, and we were possible to cross the river. Not we can't cross the border, only our equipment. This is red, this is acoustic Doppler current profiler with a radio remote control, yes, thank you. Yes, and from Russia and from Estonia, we did this simultaneously at the same time with a 5 minutes break between measures. So our Estonian border guard just here, 3-5 person, and from Russian side microbus with also with this control. So I didn't. So I told you about the problems, and we used different methods for runoff estimation. And you know, the water quantity is the basis for water quality estimation. So when we have water quantity, we multiply it with a concentration of pollutant, and we get in the end pollution loads okay, these dirty things which are not helping for our environment. In Estonia, we have a monitoring station in our city, and we measure water discharges. In Russia, they estimate the water discharge using electricity production in Narva hydroelectric power in Narva, in Ivangorod. And the difference between our measured discharges and their measured discharges sometimes was up to 30%. So, and usually it was less. The water they used was less than we actually measured in the river. It means that if you multiply smaller value onto concentration, you will get less pollution. If you multiply bigger value, you will get more pollution. So, and then you have to share this pollution loads and the ceilings, etc. So when we measured simultaneously all these discharges, the difference between our and their measurement was less than 5%. So it is acceptable in hydrology. It's excellent result. At the same time, Narva hydropower plant showed discharge about 100 cubic meters per second less when we measured. So no comments. And now, okay, this is Narva River catchment area. All this big area, it's area of 56,000 square kilometer. It is larger than Estonian territory, which is 45,000 square kilometers. But Narva River itself, it sources from Lake Peipsi, that blue one, and it lengths only 77 kilometers. And but all pollutants, of course, like, you know, it cleans our waters, but still many pollutants flow through Narva River to the Gulf of Finland. So initial data we used, first of all, Estonian monitoring data long term. In Narva monitoring station started to work from 2003. So until nowadays, it's still working. Then we used long-term discharge data in the Narva River source. It is Vasknarva, it was not here mentioned, but we used them. Then we used measured discharge data we get from the project, during the project. We also installed temporary in the tail water of Narva hydropower plant water level recorder to observe this water level fluctuations. Then we also used data from Narva years, so it is a marine monitoring station in the river mouth. So we used many data to analyze differences. And yes, the next one. And the differences we obtained were huge. For example, daily discharge in Narva river in Narva city varies from 346 cubic meter per second to 861 cubic meter per second, not at the same time, but with very short period. Sometimes Narva hydropower plant reported that their discharge is 400 cubic meters per second, and our monitoring station measured that it is more than 800 cubic meters per second in the spring. Then in monthly discharges, these differences were up to 30–40%. And even in annual water discharges, this difference is very huge. And this is not only because of different estimation method, but also because of backwater effect from the sea. So the sea impacts these water levels in Narva river, in Narva city. So we tested different methods to estimate water discharge. It is, of course, the classical discharge rating curve, but due to water levels are affected by the sea, so we couldn't find any good relations. So then we discharge rating using the velocity index method tested. Yes, it was good, but it needs very frequent discharge measurements. So at that time, impossible. So then we use discharge rating using slope as a parameter. As we have unsteady flow, we have to use this, and also linear interpolation. And this the third one, slope as a parameter to estimate this relation between water discharge and water level was the most appropriate method. So we to justify this method, of course, we started to deal with this method. We constructed these slope curves for different water levels measured in Narva city, where still this marine impact very big. For different slopes, for different surface water, surface waters, yes, were estimated, so different slopes depending on water discharge. So water levels, slopes, and water discharges. And here are they are on one figure, and it was result was very good. The best result, of course, was obtained when we used water levels recorded on the tailwater of the hydropower plant. This place where this not backwater effect reached, and we all these relations approximately we expressed by this equation. Of course, I'm not going to explain you details. It is not so easy like this equation, and that's all. Many analyses were done before, of course, and this approximation quality characteristics are here. So at least we received some relation between water slope, water levels, and water discharges. In the beginning, so as you can understand, we were dealing with unsteady flow, but first our results were received just using flow as a steady flow. And this Xi is a parameter that estimates unsteadiness. And if it less than 0.05, we deal with steady flow. If it's greater, so it is unsteady flow, and in our case it was greater than 0.08. So, and finally we received all these relations, dependency of the water slope on dependency from the water level in this tailwater of hydropower plant. It is here, and it was described by this expression. HEPS, it is hydropower plant. But Russian colleagues shorten it like HEPS. It is hydroelectric power station. We used HPP, hydropower plant. So, and the second figure is characterizing dependency of water discharges on water levels of steady flow. So this is here. Well, as you can see, okay, even don't look on these long equations, but figures are very nice. So it's very, very good relations. Yes. And to calculate water discharges during periods of intensive daily regulation with pronounced unsteadies of the flow, the John's equation, so hydrologist know this equation was used. It is here. ST index means steady discharge and slope, and delta I, this is observed slope, is observed observed slope, okay, observed slope and ST means steady slope for steady flow. And values Q is water discharge, and I is slope. They were determined from hourly observations on water level according to dependencies on those previous slides, those two big or long equations. And the values of delta I or delta slope changes are determined from hourly health observations of water levels in the tail water of the Narva hydropower plant and Narva city hydrological monitoring stations. So we recalculated water discharges using our harmonized methods, and also compared these numbers with numbers which, with values which reports Narva hydropower plant in the one world. This is harmonized method we developed, and this is Estonian monitoring hydrological monitoring station data for some years. The reconciliation of the table, and these are differences for different years between our method and monitoring methods. So there is no comparison with values of Narva hydropower plant, but you can see here. So I took this slide from final conference, and the presenter was Russian colleague. So well, but anyway, we can see that difference. These are in percentage, can be sometimes larger or greater, and not they are not always with minus. They sometimes can be with plus. So we did these recalculations for the period from 2003 to 2020, and actually, if we use these data for pollution load estimations, which enters into the Gulf of Finland, the situation looks a little bit another. So, yes, and we also produced, as I said, recommendations for water discharge measurement, for runoff estimation methods. So, in order to avoid any conflicts with Russian colleagues, we simply agreed that we will use arithmetic average. So we take water discharges measured by Narva hydropower plant in Ivangorod and measured by our Estonian monitoring stations. Sum them and divide into two, and that is compromise. Took samples, water samples from Narva River at the same time by the same equipments on two sets, two cross sections, let's say, 12 kilometers from river mouth and 6 kilometers from river mouth. One of this location actually is fixed places for water sampling fixed by Estonia, Russia, transboundary joint commission on, do you know the full name?
Joint Commission on Protection of River Narva and Lake Basin.
Yes, it's so, and we also and these data usually they are in international exchange, they are possible, and we measured we took also samples from this internationally agreed place. Then we selected one more just a little bit lower from this wastewater treatment plants where because we were taking into account also pollutants which enters into the river from wastewater treatment plants in Ivangorod and Narva city. In the firstly, we did lab analysis here at our university, but then each country did them in their lab. So we analyzed total nitrogen and total phosphorus and these additional parameters which were possible in field conditions. And standards, of course, we tested, we agreed with methods, with sampling equipment, frequency, procedures, etc. So all these data were very well comparable. So, and when we did that, so we received the interesting picture that nutrients distribution, nitrogen and phosphorus, they are not the same from the Russian side and from Estonian side, as they flow more fast from Estonian bank. So it brings more pollutants closer to the Estonian bank. So it's interesting. And we also found that this place, which is actually agreed by two countries by this commission, it is not representative for Russian colleagues. It shows less pollutants that actually exist. And one of our recommendations was to move this site a little bit lower, the downstream, because it is not representative. So as we measured these charges, we tried to associate them with these pollutants, and we found that distribution of pollutants, as I said, in agreement with flow speed, but not with how to say river depths or distance from the river bank, etc. So actually, it was our proposal, but it's on the paper. Look, this is a coefficient from Estonian side, as I said, flows more pollutants than from Russian side. But we had only 6 samples. It is not enough to conclude that our results are true. So because I think there are some tricky moments also exist. So, and water quality index, you know, it's a single number which gives us information about water quality. It's so easy. And we used one method. It is so-called Canadian water quality index method. And we modified, of course, we played with these factors, F1, F2, F3. These factors here, one is scope, another frequency, the third one is amplitude, yes. And we also, this is a scale for estimation of water quality for Estonia and Russia. And it is not in agreement with their standard or with our standard. We produced our own standard. And this is quality of our rivers. And we tested all rivers within this huge catchment area. We, of course, our experts from both countries selected these parameters. We will use for calculation of water quality index for different types of rivers, the next one. And we received the results, which are shown here. And the red one is bad, very bad water quality. It's Russian rivers, Estonian rivers, and the blue one is excellent. And what is good, that Narva River water quality is very good. It's good. It's. I think it is thanks to wastewater treatment plants which are working in Narva city, and last year's also in operation in Ivangorod. So, but on all catchment areas, situation is not so good. So believe me. And okay, the next one. So we also produced maps. We compared pollution load estimation methods used in Russia and in Estonia. And this comparison gives us different results. So our methods are different, and we also have different values in the end. And more phosphorus flows from Russia, and more nitrogen flows from Estonia. And this is very logical. It is because of natural conditions, but phosphorus, it goes from Russia. They are the phosphorus productions, yes. And these are shares. We did this estimation from different land types. Agriculture, of course, is a main nitrogen pollutant, and phosphorus is in industry and our activity as well. Yes, and humans. We have to eat a little bit less meat. Because more than 60% of our grain goes to the animals. They are main eaters. So in the end, just a few words about communication and visibility. So we organized 4 eco-marathons. Art, sport, Ecolab involves sites in Narva and Ivangorod. Also competition, teaching excellence, etc. And all this information is available on Russian language, narvariverpro.org, and also in English, Narva WATMAN.com. So we produced a lot of research. Here is 2 research papers already. They are in pipeline. Actually, they are published in Russia. So 2 published in international journals, 2 in Russia. So 3 master theses, 4 PhD students, more than 5 professors participated in our project. Yes, the next one. So challenges. So what to say now? If it's already past COVID, of course, changed our plans, and not enough data, not homogeneous data. Field measurements were sometimes impossible due to this situation. We couldn't cross the river, so we couldn't pass, actually. We couldn't transfer something through the border. And perspectives, now they are not actual. So by this, I complete my talk.